Hi, we continue introduction to nanotechnology. Photolithography is used to transfer design on the surface of a chip. Many times on the surface of a chip, we have grown an oxide. The oxide is the natural reaction of oxygen with a lot of hard surfaces, a lot of materials. We call it rust. So it's nothing but an undesirable interaction between oxygen and a number of different materials. In case of silicon, the native oxide, we call it native oxide, is a very thin layer, 25 angstroms, which is about 1 10 raised to 1 minus 10. That's an angstrom. This is about 25 angstrom thick, which grows because of the ambient conditions, the oxygen in the air and room temperature. Now, when you say room temperature, it means that oxidation or the rate of oxidation can be changed by changing the oxygen content or by increasing the temperature. We will discuss that today in this lecture as well. Now, why do we use silicon dioxide? Silicon dioxide is a very good insulator. It has very different properties from silicon. Silicon with very small amount of uh, N-type or P-type dopants, we can make it uh, very conductive. But silicon dioxide is insulator, stays very good insulator, whether there's doping in silicon below or above it. Now, this is one important property. The other property is that it is of very high quality. The thin film of silicon dioxide can cover a very broad area with very uniform thickness. And we can control the thickness very precisely while we grow oxide. Now, when you say we grow oxide, we literally use up silicon and we convert it into silicon dioxide. Why do we grow? We use silicon dioxide in many different capacities. Here, this chart shows that if it's 10 angstrom, that's just oxide, which is what we call as native oxide, which may happen during the cleaning process or during any heat treatment. But then 100 angstrom would be what we would use as insulator in the gate area of a transistor. Transistor, we know there is source, drain, and gate. Three parts. So gate is where we have to grow very thin oxide. You can make a thicker oxide, and that would be what you call as masking oxide. Oxide which we may use to cover a whole range of area just to mask what's beneath, what's below. Or you can use it as field oxide, which is 1 micrometer thick. And the reason is we want to like cover the whole field with oxide, just cover the whole thing with an insulating material. Now, oxide, silicon dioxide is nothing but glass, silica glass. So, which means that silicon dioxide also transparent. So when you grow that, we can see what's below. So it's always easy if you're doing lithography, a next layer of lithography that we can easily see through oxide and see through what's below that surface. Now, what is the difference between glass as we know it, like I have glass in my glasses, or glass of silicon dioxide that we grow on silicon wafer? The answer is in the how the silicon and oxygen bonds are made in that material. So if you would look at this graphic, it's given on this slide, you would see that a single silicon atom is bonding to 4 oxygen ions at each of its 4 vertices. And that would be what would be true for what you call crystalline silica, very fine silica. You know, when I use silica, silica is nothing but silicon dioxide, another word for silicon dioxide. Now, this would mean that oxygen ions would be shared between uh, 2 tetrahedra, so 2 shapes that are made because of silicon and their binding with the next oxidant. And this would result into a long range order. Now, another type of silica, what we call as amorphous silica, there is a combination of bridging and non-bridging oxidant atoms, and very little long range order is there. So that results into what we call as less dense glassy network. And the distance between silicon and oxidants are very precise. We know they are 1.16 nanometers, or another way we can say is 1.6 angstroms. And similarly for oxidant, it is 0.227 nanometer. Now, if you think about the densities or how many of these atoms are there, the densities for quartz and amorphous are quite different. So this quality of how the oxygen bridges is what gives us a very good insulator, which has a very good interface with itself and the silicon that's below. You know, we said we grow silicon, so essentially we would have the surface of silicon and we would start having oxygen species reacting it and then resulting into silicon dioxide. And during that process, we can introduce some elements into it, like boron or phosphorus, which what we call as network modifiers. So they would make it less strong so we can do the processing easily. Or they can make it strong depending on whatever type is the use. Maybe we need a field oxide, or maybe we need a gate oxide. So that's what our recipe would define, that do we need too many bridging oxygen molecules, we need non-bridging, or we want to have hydroxyl groups, because they would, if you have hydroxyl group, then which means a number of hydrogen atoms will be reacting with oxygen. With results, there will be a number of oxidant species will be non-bridging, and that will weaken the oxide. Now, when we said that it has very different properties, so here are a few examples of what properties are different between silicon and silicon dioxide, and why would they matter. For one, the dielectric constant is different. We know capacitive or electrical properties depend on these values. We see that it has a very high resistivity. That's why we're calling it insulator. It has melting point, which is really, really high, 1700 degrees centigrade. Refractive index is different. So there are a bunch of properties which have made silicon dioxide the material of choice. For example, the dielectric constant makes it a wonderful material for packing as metal oxide semiconductor capacitor. So this is the insulator in that capacitor, MOS, which is nothing but the gate area where you have metal on one side, you have silicon on the other side, and we have silicon dioxide, a dielectric material there. But the value of you keep on making them thinner, which have resulted the problem that silicon dioxide has become too thin physically. Hence, we have to replace it with other materials, high K dielectric materials. But that's something which if you study silicon dioxide or gate materials much closely, then we get into that. For now, we'll look at how we make silicon dioxide. So silicon dioxide is grown in furnaces. So these are long tubes where very clean tubes. There's no species, no elements, no metals in there. It's super clean. And we heat them up and we place silicon wafers in very clean, precise order. And we push them in those tubes, and the temperature across the tube is very well maintained. And then we introduce oxygen or water. So in both cases, we use the vapor of oxygen, or we use the the water. And the end result in both cases is the silicon gets rusty, silicon gets oxidized, means the same thing. But here what we are doing is we are changing the surface silicon atoms into silicon dioxide. We keep on supplying those oxidizing species. They have to diffuse through, get to the lower level of silicon, and they keep on using pure silicon and converting it to silicon dioxide. So in this process, as I'm saying, as the silicon dioxide becomes thicker and thicker, the oxygen has to now travel through a thicker layer to get to the interface so they can react with silicon and convert into silicon dioxide. Hence the last bullet point, that the silicon oxidation slows down as the time goes by, as the thickness goes up. Now, this is something which we have to study with the equation and come up, understand the model of why this happens. So this figure is something which is just to show that the oxygen species coming from the top, when this oxidation starts, so there's just silicon, it would consume silicon, return into silicon dioxide. So you have the quartz kind of a network. But now the next oxygen has to squeeze through, has to what you call diffuse through to get to the next silicon molecule. So this thickness, what we are saying, goes up and the reaction goes down. How do we understand that? So this is an oxidation model which was proposed by Deal and Grove in 1965. Both were at Fairchild Semiconductor, the forefather of Intel and all semiconductor companies. And what it does is it explained the experimental data of that day. So essentially, there are three basic components of that reaction of oxygen. If we start from left, the oxygen species comes in, it encounters the existing oxide, which has already been grown before. Now it has to diffuse through. If you see the y-axis, that is concentration of oxidation of oxygen. At the surface of the chip, it's highest oxygen, whatever we have supplied in the tube. But now when it diffuses through, the concentration goes up, and once it reaches to the interface of silicon dioxide and silicon, then there is another concentration. So in all these three regions, there are certain properties that go into designing or defining that model, that equation. We have to understand there is when the oxidation starts, the reaction is only at the surface. But once it becomes thick, now there is a diffusion regime where oxygen has to diffuse through the existing silicon dioxide, and then it has to get to the chemical reaction where is the interface, and there it has to then, first it has to diffuse through and then result into oxidation. So we define these three regions, and if you can see, there is, with the depth inside, there is F1, F2, and F3. There are three fluxes, the flow, the number of atoms or number of molecules per centimeter square second, going through per centimeter square area in 1 second. So that's these are very important factors, F1, F2, F3, the diffusion coefficients. They will help us, these fluxes, they will help us understand how reaction occurs or how oxidation progresses. So F1 is the flux from the bulk of gas to the gas oxide interface, the oxide that's already been made. Then F2 is the diffusion through the existing oxide, and then F3 is what is actually the chemical reaction occurring at the silicon dioxide interface. Now, all three have different dependencies. The F1 is simply dependent on what is the surface concentration and how fast is it uh, interacting. Number two is the depends on the diffusion coefficient, hence the D there. And number three is nothing but the rate of reaction at that interface. Now, if you take this fundamental relationship and suppose we say they all fluxes are same, we get an oxide growth rate equation, which is a differential equation with a simple second order solution, X, the X oxide, so thickness of oxide. Now, this is a very important equation because this, here we have defined A and B and other fundamental uh, parameters. So those are given on the right hand side. What we will do is we will focus on A and B and of course time and thickness. While we are not ignoring the underlying parameters, but we have the definition of those underlying parameters, which we can refer back to understand it, the relation between F1, F2, and F3. Now, what is important? What are we trying to achieve? We want to find a framework, a relationship where we can calculate the oxidation thickness for any given parameter. And parameter would be the rate of how fast we are supplying oxygen and what is the temperature for that reaction. So if we relate back to the original three regimes, so we have to understand how oxygen gets to the interface, F1, how does it travel through the oxide, F2, and how does it react at the surface of silicon dioxide and silica. Now, there are different ways how we look at it. If you do very short oxidation, which means that, yeah, we have a linear relationship, which means that whatever comes in, whatever oxygen comes in, reacts with silicon. So the equation reduces to this linear relationship where we are using B over A. It's a linear rate constant. Now, if you define B over A from this relationship, we can reduce it much further. And what we get is, because we will use H much greater than Ks, we get a linear growth regime. So which means that short oxidation would have a linear growth of silicon dioxide thickness. Now, if you do long oxidation, that relationship reduces to a parabolic form where it just depends on B. Now, B is proportional to the diffusion coefficient in oxide D. Go back to that relationship, we see that B has a direct relationship with diffusion coefficient D here in third equation. Now, if we have that, which means this is a parabolic relationship, which means, and I've shown a parabolic relationship here that as it goes thicker, the thickness increase goes down. For longer oxidation, the thicker the oxide, the longer it takes for the oxygen to diffuse through and reach the interface. So hence the overall oxidation growth decreases. So in a real oxidation, then there are two regimes. One is a linear regime and then there is a parabolic regime. So initial oxidation is faster, but then the oxidation rate goes down. So how do we find these parameters, B over A and these parameters which are given here? We experimentally get these numbers. So there's experimental determination where we can plot the experimental data and then we can find activation energies. And activation energies is a special relationship called Arrhenius relationship, which is we take the initial conditions and then it has an exponential dependence on temperature. So, and this takes the shape of these two plots which are shown here. I will not go into details, but the take-home message here is we have the values of B over A, and we plug into our relationship, and we can find linear rate constants and parabolic rate constants. Like it's given here that we can find out exactly for any temperature, for any orientation of silicon wafer, what would be the linear weight constant for those given conditions. So if you see here, there is dry oxidation, there is wet oxidation. Remember, we have two types of oxidation where we introduce just oxygen or we introduce water, and that water results into the oxygen being used. So we get these two rate constants here, and we can have a relationship, make a table from that, and this data can plug in directly into these for long oxidation or for short oxidation or for an overall equation like this equation which was given for the D group model. So we can plug in D over A and B, and we can exactly know what would be the thickness of oxide for given temperature for given time. So these are uh, fundamental ways of how we ascertain and plan our oxidation run to get certain thickness in our chip.